right? Okay, so today I want to talk to you about looking at to do some analysis on these equations, right? So what we will discuss is if we have these equations and you want to study various kinds of behaviors of the equations, and you will have seen already in the simulations you carried out with the Hodgkin-Huxley that the kind of behaviors that you expect to see are stationary states, and you expect to see oscillations and so on and so forth. Now can we try to make sense of where these oscillations arise from, what are the conditions under which stimulation will lead to oscillations, what are the conditions where if you stimulate it will not give rise to an action potential, and so on and so forth. So what we're looking to understand is to get an analytic sense of what these what are the possible behaviors in this model system. Okay. Now I will use a particular flavor of doing things, which is to be very geometric about the analysis. I won't be solving the equations in the sense of an analytic solution to the full differential equation and so on. As far as I know, no one's ever written down an analytic solution to the Hodgkin-Huxley equation. What we can do though is to study a qualitative the behavior of the differential equation, the dynamical system qualitative, and that gives us a lot of insight into how these things work. So there is going to be a way of organizing our thinking so that we can understand the behavior of the neuron. How many people are familiar with qualitative theory of differential equations? How many people have seen things like phased planes, nullclines, direction fields? Raise your hands, please. Oh, so many of you are already aware of this. So I don't have to give you too deep an introduction. For those of you who are not completely familiar with it, it will become clearer as I go along. What we'll draw are pictures describing the dynamics, but those pictures are rooted in understanding the geometric behaviors of the system. So they're rooted in underlying geometric structures that help us explain the dynamics. Okay, so let's start. I'm going to use a neuron. So let's take a pop quiz to ask what kind of neuron might this be. This is known as a Morris-Lacquer model. You can see there are two differential equations over here. Do you think these equations are recognizable? Can anyone tell me what the equations are? There are only two of them, which will be useful for us in a minute. They look like the Hodgkin-Huxley equation. You mean this min f v? Okay, that's good. That's a good point. Anybody else want to suggest something? Right. Are what? What variables? What physical variables do you think they represent? V is likely to be membrane potential, right? And do you recognize W? It's a changed notation, but do you think you recognize what W might represent? Gating variables. Correct. Right. So W is a gating variable, just like we had MH and N in the Hodgkin-Huxley. Right? Okay. So this is a two-dimensional model. This is a two-equation model in which we have the usual Hodgkin-Huxley like differential equation. Of course, min f seems to be an interesting term that is slightly different from the usual way in which we've been writing this thing. So I will leave it to you to think through further what might this mean. This is a gating variable. Now this is the equation of a gating variable, right? And that looks familiar to us. So I will leave it as an exercise for you to figure out what the physical content is to satisfaction over here. But
in the last one, we give the simulation of Hodgkin-Huxley. Consider phi as 1.
Right.
So here phi has given us 0.04.
Correct.
So phi equals 1 there, and here it is 0.4.
So phi is a variable that controls the effects of temperature, and in this case, we choose it to put a different value from 1. Okay, so these equations correspond to a model in which there is voltage. Can anybody guess by looking at the voltage equation what kind of channels are there in this? In calcium and potassium. That's correct. That's right. Calcium, potassium, and leak. So you can notice that there's a This is a clue that there is a potassium channel here. This is a clue that there is a calcium channel in there, right? So this must be a variable that corresponds to the calcium channel dynamics. Okay, so that's what I'm going to say over here. And now I'll leave this file and I'll give it to you in this thing at some point to play around with this in XPP and so on. What I'm going to show you here is that if you have this model, the Morris-Lacar model, it simplifies things a little bit. What it does for us is it gives us a way of looking at this dynamics in a plane. It's a two-dimensional model, so we're going to be drawing phase planes. In other words, I'm going to be drawing W versus V diagrams, not V versus T, not W versus T. I will draw a phase plane, a W versus T diagram, which will help us discover what the behavior of the solutions is going to be. Does that make sense? For those of you who have not seen phase planes before, this will be an interesting way of looking at the solutions of the differential equations. At first sight, it looks that there is nothing that we can do if you don't solve it, but that's not completely true. Okay? And there are nice facilities in XPP that will help you understand the phase plane behavior. So I'm going to show you, I'm going to open up XPP in a minute and I'm going to show you how to read and work with those structures that appear in the phase plane. Right? Now, there are going to be two variants of the Morris-Lacar equations, and these sentences look new to us, but in a minute I'll show you what this means. What this means is I'm going to be able to pick this set of parameters as one behavior, one type of the Morris-Lacar equation, and in another case I'm going to be able to pick that set of parameters all in all going together as another kind of Morris-Lacar. So think of the Morris-Lacar as having two types. There's going to be a type 1 Morris-Lacar, there's going to be a type 2 Morris-Lacar, and we will see that the actual behaviors in type 1 neurons and type 2 neurons, or type 1 Morris-Lacar and type 2 Morris-Lacar, are actually going to be different. And this was a physiological fact that was known a long time ago, even at the time of Hodgkin and Huxley. People knew that there were two types of behaviors in neurons, and they call them type 1 neurons and they call them type 2 neurons, right? And our modern version of this is to look at the Morris-Lacar type 1 and Morris-Lacar type 2. Obviously, we are calling it type 1, type 2 to reflect that these are representative of type 1 neuron behaviors and type 2 neuron behaviors. So my goal in this lecture is to show you what are the properties of type 1 neurons and how they differ from the properties of type neurons, and to develop a phase plane analysis that will give us a handle on these properties, where they are arising from. Okay. So the underlying basis of things will be, there will be geometric structures that will be different if you choose different sets of parameters. If you choose the set of parameters corresponding to type 1 neuron, you will see some patterns that will appear in the geometrics in the geometry of the model that will be different if you pick the different parameters, the type 2 parameters. Okay, that's my plan. Is everyone okay with that? So now let's jump straight into discussing some of these behaviors. So I'm going to open XPP and I'm going to start plotting a certain I'm going to plot those geometric structures that I've been talking about. In particular, I will start with plotting what are called nullclines. So let's do a bit of, can I get this slide please? Okay, let's take a look at this system over here. If you think of the Morris-Lacar equations, they are of this form. You have an equation for dB dt, and it is some algebraic function. This is the right hand side of that differential equation. It's some algebraic function of V and W. There is no T in this. There is no T on the right hand side, which means this is an autonomous differential equation, for those of you who know what it is. This is the other variable, the gating variable, dW by dt, and it is some other function of V and W. Does this make sense? This is a general way of writing the Morris-Lacar equations, or for that matter, any model of this type. This whole set of equations will be parameterized by certain parameters. So maybe I can write down the sets of parameters as part of the equations, and there will be some initial conditions V of 0, W of 0, and so on. So once you have that, you will be able to solve an initial value problem. You will be able to say that if I start with this initial conditions, this pair of initial conditions, then I will pick out a trajectory in time. Okay, does that make sense? Everyone knows? Everyone's okay with me so far? Okay, now let's look at what happens. What is the structure that corresponds to? So I will drop this P because I don't want to care about parameters right now. We will talk about parameters corresponding to type 1 and type 2 dynamics a little bit later. What happens, what do you think will happen if I look at the phase plane? So this is called the phase plane. V versus W, right? Is there anything interesting that I can get by looking over here? Let's put this equation equal to 0. Let's put dV by dt equal to 0. What do you think I get if I put dV by dt equal to 0? Loudly please, I can't hear. I'll get a curve, right? Because I'll be solving f of the V comma W will be equal to 0. So this is an algebraic equation, not a differential equation anymore. It's an algebraic equation which the solution of which will be some curve in VW, correct? Right? And what will be the property of points on this curve? This it will not quite be the fixed point. I'm setting only dV by dt is equal to 0, which means that the speed with respect to okay, so if dV by dt is equal to 0, right, and you're on this position over here, so then will you be completely stationary? No, you could move in the W direction, right? You will not have any motion in the V direction, and you will only be moving in the W direction, right? Does this make sense? So you will move only in the W direction, but not in the V direction, because dV by dt is 0, right? Okay, so you could be moving this way, or you could be moving that way. And similarly, if I were to set the dW by dt, dW by dt equal to 0, which means I get another curve. This is f equal to 0, this is g equal to 0, right? Then in this case, I will have no motion in the W direction, motion only possible in the V direction, right? Okay. It could be one of the other. I don't mean to draw a double-sided arrow. I don't mean to say that you are moving in both up and down. I mean to say it's one or the other. I hope that is clear. I hope that's not confusing. Okay. So what happens at a position, at a point where f and g are both 0? That will then be a stationary point with respect to the entire dynamics. Which means if I have, and that corresponds physically to the position of the intersection of these two curves. At the intersection of the f is equal to 0, nullcline, this is called a nullcline. This curve, it will be called the V nullcline. And this curve will be called the W nullcline. D. Notation is fairly self-evident why we call it that. And at the point of intersection of the W nullcline and the V nullcline, you put stationarity with respect to both V and W, and therefore this is going to be a fixed point. A fixed point is a point where if you start exactly, at least mathematically, if you start exactly on a fixed point, you cannot move off the fixed point, because there is no way to move in the W direction, there is no way to move in the V direction, so you will be stationary at the V position, at that fixed point position. What it does not say, however, is what would happen to the trajectory, what would happen to the motion, the behavior, the dynamics, the trajectory, if you are in a neighborhood, if you are slightly away from the fixed point, what would happen to you? That is not completely clear. That part is the subject of what is called stability analysis. you would ask the question, if you're slightly perturbed away from the fixed point, do you come closer back towards the fixed point, or do you diverge away from the fixed point, or do you say somewhere in the neighborhood of the fixed point? That kind of question is called a stability analysis, right? We won't have time to develop stability analysis in detail over here, but I will invoke this idea over and over again, and I will show you that there are ways in which XBB can be used to tell you about the stability of this of fixed points and so on. But note that the nature of the fixed point and the trajectory following, if you're at the fixed point, and the trajectory following if you're off the fixed point in the neighborhood, are two different things. One is a perturbation analysis, one is a perturbation scenario where you're slightly moved away from a fixed point and you're asking whether you recover to the original position or not, and the other one is mathematically, if you're at the fixed point, you can just not be anywhere else, because for all time you'll be constrained by dv dt equals 0 and dw dt is equal to 0. Okay, fair? Okay, so we've already started to build geometric structures, like for example on nullcline, which is a curve, another nullcline, which is another curve, the intersection of the nullclines, which is a fixed point, and so on and so forth. Now you might, the way I've drawn it as a schematic, you might think there is only one position where they're intersecting, but that need not be true. There can be more than one positions in which these curves intersect, right? Okay. Now depending on how complicated your right hand side is over there. So now these structures are going to help us understand these things, understand what the behavior in the system is. In particular, if you are stationary if the dynamics, if the voltage is stationary, what kind of geometric behavior do you expect to correspond to that? Just a quick pop quiz. If you find that your neuron is not firing, it is at rest, does that correspond to looking for a particular geometric structure in the sense of what I've just drawn in the phase plane? What would you look for in the phase plane? It would be a fixed point, right? You would look for a fixed point as corresponding to the voltage being at rest, for example, stationary, correct? So there you go. That's our hook. We are going to look for geometric phase plane counterparts of what are possible behaviors in the neuronal dynamics. Does this make sense? That's the plan, and we're going to develop this plan more and more as we move along. Okay? All right. So a fixed point will correspond to stationarity in the voltage equations. Let's move on. So the next bit that we'd like to talk about is to look for trajectories other than fixed point. The fixed point is a trajectory. It's a very it's a very canonical trajectory. It's a trivial trajectory in the sense that you're at that point and that's your trajectory for all time. It's just stationary at that point. That's what a fixed point is. But you can look for other trajectories. You could have, for example, let's say you started an initial condition over there in the phase plane, right? You could move somewhere in the next instant of time, and in the next instant of time, and so on. So in particular, you could trace out trajectories like so in the phase plane. Now notice that the time information is suppressed. The time is represented sort of like an arrow. There is no axis along which I can represent time unless I draw a three-dimensional picture. I could have projected time in this direction, and then starting from this point I would get a trajectory that winds out in time, right? If I compress that picture onto the phase plane, onto the WV phase plane, then all I can do is I can draw the curve that corresponds to how you would move in the phase plane, and draw a little arrow to say that I'm moving in this direction or that direction. So in other words, if I drew a curve like that and drew an arrow like that, I would imagine that starting at this initial condition, I moved like so in time. Does this make sense? Yes? Okay, great. So now we can ask this question: if I want to construct trajectories, how do I construct trajectories? What I can do then is the following. Instead of setting these things to 0, which will tell us only particular solutions, in particular the case where if I set this equal to 0, dv dt is not changing, the only direction is dw by dt. So let's abandon that. Seems a little strict, and let's ask for the full equations. What would be the geometric structures, the geometric counterparts or the phase plane counterparts of having the full equations for us with us. Anybody want to suggest what we might do in order to look? Remember that what I'm trying to do is I'm trying to get trajectories. I'm trying to anticipate, explain, maybe schematically draw how the trajectories will unfold from various initial conditions. Okay, and I'm looking for a way of representing these equations in the phase plane geometrically. How might I try to do that? Hmm. I can't solve. I'm not looking to solve analytically. I am looking to write down phase plane counterparts. What these are geometric objects. What will correspond to telling me trajectories? Raw vector fields. That's correct. Does everyone know what that means? No. So maybe I'll describe it. What we can do is the following. Let me redraw this. Let's try to ask, this is obviously a curve. If I start at a position over here, okay, what is this object in terms of the phase plane? What do you think F is telling me, and what do you think dV dt is? Any suggestion? dV dt is the rate of change of motion in the v direction, right? So if can I obtain F for this position? Does that make sense? What would it mean to write down something that corresponds to evaluating F for this V and this W, right? This is some V, this is some W, right? If you like to think about it, put this V0, W0 and then stick in V0, W0 over here. I can calculate this quantity over here. What do you think this quantity is? That's right. So it's the magnitude of dV dt. dV dt is the rate of change in the v direction. It could be moving this way, it could be moving this way. It's not completely clear which one. You'll have to figure that out. But you will have to figure out from the sign of this quantity. But this quantity will represent, let's say it's moving in this direction. This quantity locally will represent the rate of change in the v direction. Right? And you can evaluate it. You can evaluate it because you can evaluate F. So I know exactly what the speed is over here by noting what the F is. And similarly, for noting the rate of change in the W direction, I can evaluate it because I can evaluate G at that point over there, and that tells me how fast or slow the speed of motion in the W direction. Correct? With these two, I can then take a vector sum because speed plus direction will give you a vector velocity, and velocity is a vector, so we can take a vector sum, and that vector sum will tell me the direction of motion from this point, say at least over the next instant, at least locally frozen in time over the next time delta t dt. It will tell me the direction of motion. Okay, does that make sense? So in other words, I have been able to use the right hand side to evaluate the velocity of motion given that I have a particle over here. So these are all descriptive terms, velocity and so on. Nobody is running, it's this particle that's running, if you like, right? It does evoke the idea that if you are at this position over here, you will over at least the next instant move in the direction that corresponds to the velocity of this particle. Does that make sense? So now you are say over here, right? Let's say you evaluate it over a short time. Of course, all of this makes sense in proper sense only if you do calculus and you allow for dt to tend to 0 and so on and so forth. But it will, but the idea is exactly the same, that you're moving a short distance along the velocity direction. Now you're at this position. Now you can reevaluate this entire thing over here. Correct? Now you have to reevaluate it at the new position because you moved to a new position. Now you might find that your velocity vector has changed, right? And you move to a new position, you might find the velocity vector has changed again, or maybe it hasn't changed, but whatever it is, you have to keep re-evaluating your right hand side, your f and g, as you move from point to point, correct? So in fact, you might then figure out a trajectory that corresponds to this motion. If you take shorter and shorter steps in time, you'll be able to piece together how this particle is moving. Okay, so you'll be able to put together the trajectory. Now you can take it one step further. What you could do is, instead of piecing together, well, you will have many trajectories, right? You can start from position here, develop this trajectory. You can start from position there, develop that trajectory. You can start from position here, develop this trajectory, and so on and so forth. You can develop a lot of trajectories. Good, that can be done. Maybe you can put it on a computer, and the computer will do this for you. And in fact, if you do it in XPP, you can do it in XPP. XPP allows you to be a facility to be able to do this. So you could develop trajectories like this. There's one important thing to notice for these trajectories is they will never overlap. They will never cross each other. Why is that? They will never cross each other. Yeah.
So from that direction I cannot move any value.
That's correct. So if there was an intersection, if there were two trajectories that were crossing, then at this position I might ask, is the velocity vector, the one that I drew over here, is it corresponding to this or is it corresponding to this? And because you will violate uniqueness, you cannot have trajectories crossing, right? It would violate you being unambiguously knowing the answer. So trajectories in autonomous systems don't cross, which means that as I layer in trajectories all over the place over here, I will have trajectories that can come close to each other, sometimes even asymptotically, very, very, very exponentially close, but they will never pass through each other. So one trajectory actually serves as a boundary for any other trajectory. No trajectory will ever pass through it. That's kind of important, and that's kind of useful as well. So you can layer in lots and lots of trajectories over here and get a sense of what the motion is from a given space, from a given region. So you might find, for example, that if you start at various initial conditions here, you're going like so. That could be one possibility, or you could go around like that. That could be another possibility. So by layering in trajectories, you can get a good sense of what the general, what's called flow is in this system, right? The general pattern of motion in this system. Then there is another way in which you can look at this as well. An alternate way is to drop drawing trajectories entirely. Why do I even care to draw the trajectories? Why don't I simply draw at various points what the velocity vectors look like? Instead of drawing trajectories, I simply stud the plane with, I'll pick a lot of positions arbitrarily, maybe I'll take a grid of positions and I will draw what the velocity vector looks like. Okay. So if you do this, if you do that sort of thing, it's called a direction field. And if you draw your trajectories, it's called the direction flow. Okay. So we're going to show this we're going to use this in XPP. So now we have objects that we can play around with. We have been able to say, reproduce this in a phase plane. The essential content of this diagram has been transferred to looking for geometric objects, vectors, lines, fixed points, those sorts of things in the phase plane. Okay, does that make sense? So that's my very quick introduction to a phase plane, and now we will use this to understand the phase planes that correspond to the Morris-Lacar equation. Because what we are hoping to do is, if you look at the phase plane, you might discover what's going to happen. We already saw that one of the things that could happen is to have a fixed point. A fixed point will correspond to stationarity of the W and B variables, which means the neuron, if you started there at least, will remain at rest. Right? Now we can use that kind of information and say, ask what will happen if the neuron were perturbed slightly. If you moved off the fixed point just a little bit, would you relax back to the fixed point? And that would correspond to a stimulus in my neuron. That would correspond to saying that if I had a little current injection in my neuron, Will that current injection cause a return to the equilibrium, cause a return to the fixed point, in which case it would mean that you'll have a perturbation, the voltage equation will change and the W as well, the voltage variable will change, but it will come back down to the resting situation, it will come back down to the fixed point. That will translate to the perturbation question around the fixed point in terms of the phase plane. You could also ask more sophisticated questions. If I have oscillations in my trajectories, if I have periodic oscillations, which means I'm getting firing, and this keeps on going at a uniform spacing in time, so which means it's got a constant period and maybe it's got a constant amplitude. What kind of geometric structure would that correspond to? Can anyone think through what kind of geometric structure would you look for in the phase plane which would correspond to repetitive firing, repetitive stereotypical firing? What might that be? It would be a closed curve in the VW space. Let's see why that might be. In the VW phase plane, if you had a closed curve and say you're moving in this direction, well, voltage would increase, look at this direction, voltage would increase, then decrease, then increase again, then decrease again. So, you are getting increasing voltage, decreasing voltage, increasing voltage, decreasing voltage, and so on, right, in time. Remember I said this is a phase plane, so you are suppressing time, but you can recover the time information by imagining how things might work in the time direction. The arrow will tell you the direction of time and you are going around and down. So, when you are going like this, you are increasing the voltage, when you are going back down, you are decreasing the voltage, right. So, a loop, a closed circle in the phase plane dynamics would correspond to repetitive firing in the voltage. Okay. Now, you can ask the same question that you asked of fixed points. Yes, you have a loop. Since this is a closed loop, that means that you are always going to go wrap around the same trajectory over and over again, right. So, this is one trajectory and it closes in on itself. So, you keep going around and around and around on that trajectory. What we haven't answered here is what happens to trajectories that are nearby. What happens if you are on a position that's off this track, but you are not on the track exactly, but do you imagine then that you will go around and round from a position like so here? That is not generally a good idea to believe in, right. That happens only under very specific special circumstances. What I am trying to say is that if you start here, you do not expect to go around in a loop of its own. That is not a good expectation. Okay, it happens only under very special circumstances. So, the general expectation has to be you might come closer to the previous cycle. If this is your cycle, if this is your periodic cycle, you might start from a position that's away from the cycle and come closer to the cycle. Do you ever merge with the cycle? Would you ever merge with the cycle? No. We said in a minute that trajectories cannot touch. Not only can they not cross, they cannot touch either, right. But you can have a trajectory that comes closer and closer and closer and closer to the trajectory to that periodic circle that you had. You could have that, or you could also have then maybe you do not come closer, maybe you track it for a while and then diverge away from it. That is another possible behavior that you can expect, right. So, we are going to look for these signatures, we are going to look for what the potential behavior is. I mean, we know what the potential behaviors are, we are going to look for under various circumstances what the behaviors are, because those will mean something, those will mean physically different things. For example, you might start with a position over here and find yourself that you do not actually go closer to the periodic circle. You might find that you actually go and hit, you go closer and closer to a fixed point. That would be interesting. Well, that would be interesting for the reason that that would mean that if you are on the circle, you are perfectly winding around, right, you are exactly on the circle, then you are perfectly winding around. If you are slightly off the circle, you actually do not come closer to the previous cycle, in which case in oscillation, if you are in this at this periodic orbit, you will go oscillate, oscillate, oscillate. But if the moment you change this a little bit and you happen to be on the inside of the circle, you will actually come closer and closer to a fixed point, which means the oscillation will die. It will dampen off. Right? So that's a dramatic change in behavior. You've got a neuron that's firing if it's on the periodic orbit, and if you perturb away from it in the sense that you come into this circle over here, then you cannot fire anymore. Eventually that oscillation will be damped over. Right? So that's an interesting behavior that we are going to look for. It could happen that you perturb yourself, you perturb on this side of the circle, and you don't die. The neuron doesn't die. The neuron actually starts, instead of oscillating on this periodic orbit, it starts oscillating on that periodic orbit. Can you imagine how that might occur? It would have oscillated with this amplitude had it be exactly on the periodic orbit. You perturb it in the right manner just so that you are outside that oscillation, and boom, your oscillation increases. Okay. Can you imagine what that might do? Well, what that might be is you start here and you can actually converge, or you come closer and closer to another orbit which lies elsewhere. So I apologize for getting a little messy on this diagram. So I think it's a good time to switch to XPP and start showing you some simulations. This was just a prelude so that I can prime you to what sort of behaviors to look for, because these are meaningful in the dynamics of the voltage equations. Does that make sense? Okay, shall we start looking more carefully at the Morris-Lacar equations? Another question that will be very interesting to us is, how do you pass from being stationary to being oscillatory? I asked you to plot a bifurcation diagram by hand when you did the simulations, and what that was leading up to was to say that if I change the behavior, if I change the amount of injected tonic current into my system, the behavior of the system changes, the response of the system changes. Think of it as an input-output response. If my input is low, my response can be low. That means to say I am at a stationary position, and then there is a phase when if I increase my input a little bit, I get oscillations, right? And then in fact there is a phase, I don't know how many of you saw this in the diagram, in your diagrams. If I increase my current beyond a certain point, I become stationary again. The volt neuron becomes stationary again. Hands up, how many have already seen this in simulations? So this is a very interesting idea. You can inject a small amount of current, the neuron sort of doesn't respond with oscillation. You inject on an intermediate level of current, which we'll see what intermediate might mean, you get an oscillation in the neuron. So the neuron has a full-blown action potential, and in fact not just one, it has a whole train of these action potentials, and you now increase current beyond that, you increase it even more, and the neuron shuts down. The neuron becomes stationary again. Very interesting, very surprising behavior. So it behooves us to ask, well, what causes this passage from this stationary state into an oscillatory state into again maybe a stationary state? I for once, when I didn't know of this, when I hadn't studied this, and I saw the stationary to oscillatory behavior, I thought, maybe the neuron will just continue to fire in an oscillatory regime as you increase current. Maybe the fire will become faster and faster, more aggressive, something like that. But I never could anticipate that if you increase current more, the neuron would just shut down. That is surprising, and in fact it has interesting implications which we won't discuss here. Okay, so let's start with looking at the Morris-Lacar equation. I'm going to set it up so that I'm going to show you some of these structures which I've just verbally talked about, and then we're trying to piece together these things in terms of composing an entire bifurcation diagram of the neurons. So that's the program. I'm going to also show you how to get a bifurcation diagram by using what is called Auto. Auto is a program that was written by Eusebius Dodel several years ago, several decades ago, and it has been contributed to by many people, I believe. And what Bard Ehrmantraut has done is to provide an interface to some of the most important functions, some of the most convenient, most widely used functions of Auto as an interface, through an interface from XPP. What that means is you can start Auto auto being a bifurcation package from XPP. And what that allows us to do is I can set up my simulations in auto in XPP, and then I can pass certain features of it to auto, call up auto, run a bifurcation analysis on it, in the sense that I can compute a bifurcation diagram, and then I can grab features of the bifurcation diagram and look at its behavior in the phase plane. Okay, powerful functionality. I don't know of any other program that does it so well as XPP, but this is going to be very useful for us. What we are going to do is we are going to be able to change the parameters of, say for example, current of the model. Then we are going to be able to see what would happen if I change that parameter systematically, if I were to change the current systematically by way of a bifurcation diagram. And then I'm going to pick out spots on the bifurcation diagram, because I'd like to understand, well, how did you go from being silent to being oscillatory, and then I'm going to plot it back into the phase plane and study the phase plane structures, which I hope we can get a handle on, so that I can understand this better. Where did the bifurcation diagram come from? Okay. I should also mention that the bifurcation diagram and the phase plane are sort of complementary techniques in the Morris-Lacar equations, but there's an important point I think you should note here. Bifurcation diagrams can actually be computed for large systems. You can compute a bifurcation diagram for the Hodgkin-Huxley equation. The Hodgkin-Huxley equation is a 4-dimensional system. You could compute a bifurcation diagram. That is what I was asking you to do in the tutorial. You can actually compute a bifurcation diagram of the Hodgkin-Huxley equations more accurately using auto from within XPP as well. The phase plane analysis is limited to having a phase plane. It is limited to having a 2-dimensional system in which you want to study these geometric structures. So phase plane analyses are toy versions that help us get a good sense of what could be going on in the full system. Larger and larger systems, studying them geometrically become more and more difficult to study, right? When you go 3 or more dimensional systems, it becomes much harder to do. So what do? Well, technically you can't do much. You can only study phase plane systems if it's a 2-dimensional system to begin with, but you can use a bifurcation diagram to study higher dimensional systems. A bifurcation diagram will give you a map and you can study various aspects of it, but you can use your intuition from studying 2-dimensional systems to understand structures about the full bifurcation diagram. But there is a knowledge gap here. There is a step where an applied mathematician is required to say that the stuff that you think you are seeing in a bifurcation diagram really do arise from certain structures that are present in the equations. Okay? So what that means is that there is a good scope for doing analysis for those of you who are interested in doing applied mathematics problems of this type, that you can do a lot of good analysis in trying to understand, trying to fill in the blanks. What we see in the bifurcation diagram, is that really what we thought we saw from looking at lower dimensional systems, for example? That could be one kind of question. And there are all sorts of analyses that people do, and this is a very, very rich field of investigation of study, and a lot of scope here for doing very good applied mathematics. Okay, so there's a lot of literature on it also, and there are lots of good problems that continue to be open. So with that pitch, let me step right into looking at XPP and showing you what the phase plane diagram corresponding to the Morris-Lacar is. So let me start with Xwin 32. Could you turn off the lights, please? Yeah, can you turn off the lights so that I can use the projector? Yeah, off. Okay, projection. Okay. It's warming up. Oh, there it is. Okay, great. So don't worry about the Morris-Lacar equation, the ML.OD. Of course, this is Bard Ermentrout's file. I don't want to give you the impression that I've written it. This is a file that's written by Bard. It accompanies this book, Mathematical Foundations of Neuroscience, written by Ermentrout and determined. You can find this online, but I will also make it available through Gautam's website. At some point I'll ask him to upload it so that you can download it directly and take a look for it yourself. Okay, so I'm going to start this file over here, and by now I hope you will have a good sense of XPP, so that I don't have to walk you through every little keystroke that I punch in. Okay. This is, as it is set up, it is a W versus V plane. Okay. So even just before we jump into it, I have not changed any parameters. I'm just using the native parameters. The default parameters are there in the file and so on. Let me first plot the nullclines to begin with. That's the fun thing to do. Okay. So I'm going to go to numerics, and I'm going to go to nullcline. Oops, sorry, non-nullcline control. Nullclines. Where is new? And excuse me. I remember the keyboard shortcut. It is NN. Okay, N for nullcline, and there's something here which says N. So in the interest of time, I'm just going to plot that. But all of this is out there on Bard's tutorial website. So if you want to reproduce it, please go through this tutorial as well. Okay, so here's what I see. I see that there is this, there's this N-shaped nullcline over here, and I have another nullcline that's going over there. These two are in two different colors to suggest which one of them is one nullcline or the other one is the other nullcline. And at the moment we don't know which nullcline is which. You can probably figure it out, but we don't know it for the moment. So what can I do? How might I check what nullcline is which? What should I, if you were looking at the phase plane, what is the sort of thing that you would like to plot to see, to figure things out? Okay, so let's go plot direction field. Okay, and I'm going to take a grid of 20. Sorry. There you go. Okay, so do you recognize this? These are little arrows. This little head is the arrowhead, and that's the little tail. Now that is a plot of the direction vectors. This is called a direction field because it is plotting the right hand sides together with the magnitude and direction that corresponds the right hand sides of differential equations, right? You remember f of v and w and g v of w that I had written. So this, for example, if you were at this position over here, you would tend to move in this direction. So that is the direction vector corresponding to what would happen to a particle, what would be the velocity of the particle had you started over here, and you can do that for various positions. Now what can you look at, how do you look at this and decide whether this was the V nullcline or whether this was the W nullcline? Can anybody guess? Okay, what does that mean? So for example, what do you reckon, what do you think this is? This direction is V, that direction is W. That says over here W versus V. So which nullcline do you guess this is? I'll give you a clue. For example, look at this one. What do you think is happening to the velocity as you pass through the nullcline, or if you're on the nullcline, on this nullcline? Is there motion in the W direction or the V direction? There is motion in the V direction, which means W must be dV dW dt will be 0, and so this is the which nullcline? W nullcline. That's right. So this is the W nullcline, and notice here, for example, you see this vector. When you're passing through this nullcline, this vector has a velocity that passes only in the W direction. There is no V velocity, right? Which means this must be the V nullcline. And in fact, at every point on this, you will have dV dt is equal to 0. At every point on this, you will have dW dt is equal to 0, which means you can pass across the green nullcline only in the horizontal direction, anywhere you are on the W nullcline, and you can only pass through either this way or that way. in the vertical direction if you're passing through the V nullcline. This is a very important idea. Okay, so this is going to be this funky N-shaped nullcline is your V nullcline, and this is your W nullcline. The W nullcline, if I plot it fully, it will actually have a shape that looks like this, something sigmoidal, if you like. Okay, and we are looking at this position over here. Now, if you start over here, for example, how do you think you'll move? Just as a quick check on the sorts of things that I was drawing on the board, but now this time it's computed with the with XPP. What do you think will happen? What do you think will be the behavior of a trajectory that starts over here? Anybody want to trace it? Help me trace it. So I would move here, then I would tend to move in this direction, then I would tend to move here, then I would tend to move here, 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 something like that, right? That's what my guess is. Okay. No, that's jumping a little too far. I'm at this point, I'm just trying to see if I start here, it seems like I would be passing like so, and maybe I'll cross this, and maybe something happens over here, but I'm losing resolution in what the direction is. The velocity is becoming really small, right? That's why the vectors are becoming tiny, 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 and I can only see the head of the vector, so I really don't know where it is going. And something seems to be happening where things are slowing down tremendously over here. Obviously, the things are moving very fast over here, right? Long vectors, long velocity vectors. It means the velocity vector, the size of the vector is proportional to the velocity, right? And XPP is doing a very clever job of scaling it appropriately. So velocity over here is obviously lower than the velocity over here. So I'm moving fast over here. I go zoom, but then when I come here, oh, I'm slowing down, right? Okay, so let me check that. Okay. So I can, there is a initial condition and mice, which gives me a way of clicking on the phase plane and figuring out what the trajectory is going to follow. Okay, so take your best guess. I'm going to click somewhere over here, okay, where this arrow is pushed. Okay, how many people think it's mentally think it's an oscillation? Things will go around in a circle. How many people think it'll go fast and then it'll come into the slow zone and die off? Okay, take your own guess. Let's see what happens. There you go. That's what happens. Okay, it has the right sorts of behavior that you wish it to happen. See, it moved here, which is following the arrows, correct, good. It passes vertically through the V axis, good, because that's what the V nullcline is saying it should. It goes through, follows the arrows, passes horizontally across the W nullcline, good. It passes through, happens to land in this region where it now has to go through the V nullcline vertically, and it never quite gets into this region over there. It turns around and its velocity is dying, so it becomes closer and closer to this point. Why did it happen? What do you know about this point over here? It's a fixed point, right? A fixed point doesn't guarantee that trajectories should converge towards them. That is the stability question, but a fixed point does say that if you're at this position over here, you're going to be stationary, right? So in fact, I could check for a point that started over here, and you won't see that, literally you won't see that move, because it's so close to the fixed point that it just barely wouldn't move, right? This trajectory over here is becoming technically it's becoming asymptotically close to the fixed point. As you approach it, it slows down. This trajectory, as you come closer and closer to the fixed point, it slows down and it's headed towards the fixed point. In particular, I could look at the stability of points here. So I'm going to click in this region over here and ask what happens to trajectories that are close to the fixed point. Okay, just because one trajectory is coming close to the fixed point is not a guarantee that all trajectories will come close to the fixed point. Right. Correct? So, but if all trajectories in the neighborhood are coming towards it, well then asymptotically, I think that is to say you wait long enough in time, then that is a stable position. That's a stable fixed point because it's attracting all the trajectories in its neighborhood, right? Okay, so let's go and click. Okay, another one, attracted. Okay, let's keep clicking. Wow, look at that. Almost nowhere and it's a local stability argument. This is not saying that I can start here and still get attracted over here, not necessarily. This is a local stability argument. This says that if I start locally in the neighborhood, what happens? Okay. It is not obvious that you should always expect all trajectories to just converge to the fixed point. That's not going to happen. Okay. That is not in general a good expectation. That is the perturbation analysis that you have to carry out to figure out whether or not trajectories will get attracted to it or not. But here locally we find that trajectories are all getting attracted to this fixed point. So, this fixed point is called a stable fixed point. Okay. Does that make sense? Okay. And in fact, I just said a minute ago that it's a local stability analysis, which tells you a local stability analysis is a formal way doing applied mathematics. You can come up with a formal way by looking at the eigenvalues of the Jacobian matrix and so on to guarantee this kind of behavior. So, there is a mathematical check that you can do, but it's a local, but that local stability analysis does not tell you what would happen to a trajectory starting over there. So, that's an important distinction to have. There is a global motion of the trajectory and then there is a local motion of trajectories. A perturbation analysis that is carried out by a local stability analysis tells you what happens locally over here. It does not tell you what would happen over here, and that's the difference. That's why we study phase planes, because we would like to understand not only stuff that would happen locally, but we would also like to understand in the big picture away from the fixed point what would be the nature of trajectories. This, for example, what do you think it would look like if I were to plot it against a V versus T diagram? So, I am going to plot one more trajectory. I am going to say plot it from here. That didn't do anything from, look at that, amazing. I started here and then I started just a little bit away, hoping that this trajectory went and died over there. Maybe somewhere close by will also do the same thing, but no, voila, look, it happened it went all the way over there, then turned around and came back. It didn't just go boom down here. What do you think the voltage would look like if you looked at a voltage versus time graph? What do you think the voltage would look like over here? Now guess it, imagine in your heads what it would look like. You would find for this trajectory over here, you would find the voltage starting at minus 40. There is not much difference between minus 40 and minus 30, but starting at minus 40, I would say the voltage went just a little bit up and then went down, correct? Isn't that what's happening? The voltage went just a little bit up and then it went down all the way to minus 60. So, that's this trajectory over here, right? What about the trajectory, the other trajectory in the neighborhood of it? Now, that started out by increasing voltage all the way up to 30 millivolts, then it turned around, look in this direction, turned around, went lower than minus 60 and then came up back up a little bit. So, this trajectory, that other trajectory went up, came down, went below minus 60 and recovered, right? That's an action potential, right? That looks like an action potential to me, right? Big difference in the trajectory in this, and so this is your first encounter with what is called excitability. Excitability is the idea that if you have a little bit of a perturbation, you can have a bit of a jiggle, a bit of a response to it, but that response is not substantially large. But then there are ways, but then if you increase your stimulation, if you increase your stimulation so that you jump just a little bit into the right kind of phase regions, just a little bit more different, then you actually go through a very different trajectory. You go through an excitable region of the system, you go through, so this is excitable, you go through an excited region of the system and then come back down. So, the trajectory behavior is very different, even though the two starting points seemed very close to each other. So, there is a sort of threshold behavior that's taking place. You seem to have crossed some threshold over which the response is now completely different, the action potential response, rather than just a little bit of a perturbative blip response. Does this make sense? So this is called excitability, and it's a big field to study in computational neuroscience departments, in physics departments, to study the behavior of excitable media, to study the behavior of excitable systems. Okay?
Can you say that the distance between fixed point and the point from where you have started to draw that graph, that is the amount of excitation?
You need to get an excited system. Is that what you're saying?
Yeah, you have told that about excitability.
Yeah.
So it will depend upon the amount of input response. That means amount
Yes.
of excitation.
Yeah.
So is it related to the distance is related to the amount of excitation?
Okay, it's not quite as simple as that. He's asking if I can come up with a simple way of classifying my excitability as, you know, simply being how far apart you are from the fixed point. In one sense, yes. In another sense, no. So yes, in this case, you know, it turns out that there's actually a curve, and if you're on that right side, on the right hand side of this curve, you move into this excited region, into this excitable trajectory region. If you're on the left side of this curve, you will move towards the thing. So yes, in some sense this is true, but that it's a lot more nuanced than that, and what I'm going to show you will bring out the nuances of what excitability means in these systems. There are different ways by which you can cause a system to be excitable, and that will cause the difference between type 1 and type 2 neurons. Okay. So my goal is going to be over today and tomorrow will be to show you the different ways in which excitability can come by, and at least the simplest ways in which the excitability is different in different models. Okay. Okay. So I'm now going to show you in the next 20 minutes or so that I have the behavior that the change in the behavior in these systems. So for example, I'm going to see how I might get this fixed point to become unstable, for example, or how I might get periodic orbits to appear in this system, because look, as it stands, there doesn't seem to be any periodic orbit over here, right? You want proof? I'll just click on a lot of different trajectories and see if you find a periodic orbit, right? So let's see. Anybody want to suggest any region where I might be able to find a periodic orbit? I'm just clicking arbitrarily all over the place. It seems like no matter what I do, no matter what I do, I'm eventually coming closer and closer to the fixed point. I can go through an action potential like sequence trajectory, but I end up landing here over there, and so no matter what I do in the phase plate, there doesn't seem to be any closed loop which I'm getting attracted towards, which seems to be cycling over round and round, right? So then the question falls to us: how might we find periodic orbits in these systems? Right? Anybody want to take a quick guess? What will I need to change in order to find a periodic orbit? I0. You change parameters? Correct. So you might change I0, for example. You might change the applied current. Now, the applied current is a way of stimulating the neuron. Right? It's a way for us to study under changes of the parameter. If you like a differential equations language, if you change the parameter, how does the behavior of the system change? If you like the biology interpretation, if you change the current stimulation, what is the output of the neuron? What is the output response of the neuron? Those are equivalent statements now, correct? Okay, so I am going to now change the input current, and I'm going to be able to show you what how the behavior of the neuron changes. So let's halt our foray into the phase plane diagrams. We'll come back to them, but let me first now skip to showing you how to compute a bifurcation diagram from XPP. I'll start with these equations, and I will compute for you the bifurcation diagram of the Morris-Lacquard under type 1 type, and I will compute the same bifurcation diagram for you under type 2 type. This will tell you two things. One, the surprise is that the two bifurcation diagrams are going to be different, which means there's something fundamentally different in the mathematics that's going on between the two types of these neurons, right? And the advantage of seeing this also is that it will give you a chance for you to try out how to do bifurcation diagrams with XPP. You can take these files and you can try to run the bifurcation diagram yourself, and it will give you a feel for how hard or difficult it is. I should say upfront that my advisor was Bar Dermot he used to say that driving with I mean working with XPP with auto is like driving a stick shift Ferrari. If you know what you're doing, you can get there very fast. If you don't know what you're doing, you can crash very quickly. So bear with me while I try to coax auto into giving us the sort of diagrams that we like. Okay. The point being that auto can be very finicky. There's lots and lots of parameters you could change with native auto. BART has done a very good job of retaining only some of the full auto features, but those are the ones that are most commonly used. Those are the ones that are most useful, at least in the sorts of things that the mathematical biologists and computational neuroscientists work with, right? So we are not going to have to tweak too many of these parameters in auto, and it would probably be hard to show you what different parameters could be. Most of them are set to good defaults, and I will show you only a few changes that you need to make in order, and we'll hope that auto will run based on these few changes. Okay, so let me shut down my my file right now, so I can start with a blank slate. I will also close xwin32, start it again, because I have a timed half-an-hour version of things, and it would be nice if it doesn't die in the middle of a computation. Okay, so it gives us 29 minutes, which should be more than enough for us to complete working through this. Okay, let's start with Maurice Lacquard. Follow the sequence of steps I'm taking, and even if you don't follow all of the details, it'll be I'll try and point out the essential highlights over here, so that you can take it up when you go back and do it yourself. So I just for convenience, I'm going to plot a nullcline. I know that this nullcline is has a fixed point. I am going to do one more thing. I'm going to click on file. I'm going to click on get parameter set, and those parameters that I had written down are actually now available in XPP to pick on as a whole, and they are named set of parameters. I'm going to talk about SNIC and HOPF. Okay, and these names will become clearer to you as we go along by their name like so. These are suggested names. Okay, so let me start by picking SN. Or let me pick HOPF to begin with. Okay. Oops. File, get parameter set, and then click on HOPF. Okay. So now the parameters corresponding to the HOPF set, which I showed you, are picked up in XPP. Those are the parameter values. Okay. I'm going to click initial conditions go. So whatever was the default initial condition, and I'm going to click on initial conditions last. Okay, those initial conditions last. What? Like, it seems like things have disappeared, right? But what's happening is that trajectory that came over here into the fixed point is now very close to the fixed point. So initial conditions last says whatever point you left off at, use that as your initial conditions to compute further. So if you're going to be close to a fixed point and you compute further starting at the fixed point, where will you go? You will stay at the fixed point or you come closer to it, right? So by clicking on initial condition last, and I'm going to do this a couple of times just to make sure that I'm really close to a fixed point. Remember, technically you're not at a fixed point, but you're coming asymptotically close to it because this is an attracting fixed point, this is a stable fixed point. So I'm going to click on initial condition last. You will not see anything happen. But I'm doing it so that I know that my starting point is very close to a fixed point. Auto needs this before it can compute a diagram for you. You need to get a good starting point. If you don't give it a good starting point, auto will fail very quickly. Okay, hopefully I am close to the fixed point. I'm really close to the fixed point because I've done initial condition last a couple of times and things don't seem to be changing. I can actually plot the V versus T and see that the things look stationary, and I can plot the W versus T and see that also looks stationary and so on, right? But I won't do that over here. A couple of times of initial condition last, I know for the system works. Now I'm going to click on file and then click on auto. So auto is now open. Okay. Notice that you've got both the XPP window and auto windows open, and in fact we are going to see that these two are going to be communicating with each other, which is fantastic, which means that I'm going to pick out structures in auto and then show the face plane. I could show the face plane in the XPP window. So this is the auto window. It says right up over here, that's auto. Okay, and there's a bunch of options on the left hand side. Don't be intimidated. Once you get a little bit familiar with it, you won't be so jarred by having so many of these things. And the nice thing about it is you probably can just pick these things, set these things up in sequence, right? So Bart has done a really good job of setting it up nicely. So let me click on parameter to show you what parameter is going to be our bifurcation parameter. I hope by now you understand what I mean when I say a bifurcation diagram, right? You understand that this is going to be on the x-axis is going to be some parameter, on the y-axis I am going to plot some aspect of the dynamics. Now I have two variables, I have v and I have w. I can plot any one of them. So in particular I am going to choose to plot v as a function of parameter. This is not time, that's not the other variable, it is a parameter of the system. So this is a diagram that parameterizes the behavior, the output behavior of the system as you vary the input parameter, some input parameter. Okay. In this case it is already known to auto that the parameter that I would like to move in is the first parameter I0. Okay. Let's not worry about the other parameters that are filled, we'll just choose to ignore them. Your question? Because that's the first parameter that's been declared in the script. Had it been any other parameter that was declared in the script, it would have picked that as the first parameter, just a default. So it's a nice trick to define the parameter that you would like to run a bifurcation in as your first parameter that you define in your XPP ODE script. Yeah, you can change it. Yeah, you can change it. There's a little star over here, probably not very clear there, but you can click on it, it will give you a drop down and you can change it. Okay, so I'm just going to I'm going to go with the default I0. Okay, then I'm going to click OK. Then it says, well, what are the axes you want to pick? So high low is something that we are going to pick. What that means is, if there is a periodic orbit in my system, then I'm going to plot the very highest point of the oscillation, and I'm going to plot, or rather auto is going to plot the very lowest point of the oscillation. So it will have one dot, another dot as the amplitude, to define the amplitude of the oscillation. We'll see that in a minute, so don't worry about it. Okay, we'll go with the usual high low, and it says, well, on the y-axis what do you want? It says V over here, that's default, and it's good because I would like to see what the voltage is doing, right? That's very useful. That's what is more informative, more interesting to me from the biological point of view. Next, this is the main workhorse. Next, I will plot. I have to fill in these numbers. Now, there's a lot of information that one can give about these numbers, but what is going to be interesting to us are these three boxes: n max, parameter min, and parameter max. What that will say for me is, what I'm asking auto to do is, you sweep in the parameter from parameter min to parameter max, which means you can set up my I0 to sweep between 0 and 2. Well, 2 is not going to be very interesting to us. I will change it to say 250. Okay. Now you can ask, well, how did I get 250? Well, I got it by I played around with XPP simulations, I played around with the Hodgkin-Huxley simulations until I discovered that interesting stuff is happening over this range. So now I know what the range is, so I'm going to set it up in my so I'm saying it is motivated by doing simulations and playing around what the range of this thing. There's no intrinsic sense otherwise. So I played around with these simulations, and I know that interesting stuff that I like to watch over is going to happen from 0 to 250. So which is why 250 over here. Let's just also change n max. N max means the number of points that auto can hold in its memory before it stops. I would like it to be able to do the full bifurcation diagram. Usually 200 is not enough, or sometimes it's not enough. I have plenty of memory in this machine, so we'll increase it to 2000, and hopefully that should be enough. Okay, so we are set most of the time, mostly. Let's click on run. Okay, let's see what it does. What I expect to find is it will start with that fixed point that I gave it from XPP. Remember that I did that initial condition last business to find a fixed point and have handed it over to auto. Internally it has been handed over to auto. So it will find that position and then it will do a continuation in I, which means it will jump a little bit in I and plot the new location of the fixed point if it is a fixed point. And then it will jump a little bit more in I and plot the new location. So I should start to get a curve that corresponds to fixed points. Does that make sense? That's what we're looking to happen. Is that going to happen? We don't know. Okay, so cross your fingers and let's see. Let's see how our Ferrari runs. Oops. I'm going to click on steady state. Right. So you see something is. Oops. Just give me 1 minute. Something seems to have happened from in the main window, but you really don't know what that is. So what we'll do is. I will go to axes and say fit. There it is. What that did for me was the computation took someplace else. My viewport was someplace else. So I moved my viewport over to where the computing has happened. Right? That means that's just an easy thing, easy enough thing to do in XPP. So you move your axes to fit whatever the computed branch of fixed points was. So these are called branches of fixed points. What each point is a dot. And the way it is computed is if I naught were held at this, then the fixed point would be that. If I were a little bit different, then the fixed point would be that, and so on and so on and so forth. So it has actually computed a whole branch of fixed points all the way up to 250. That's very cool, right? You could hardly do it by hand. You go do a simulation, find out what the fixed point is, bring out Excel and plot it. Go to the next point and find out where the fixed point is, plot it in Excel. And here in a fraction of a second, XPP's auto, when it works really well. It has swept the entire branch for you. Boom. Now you'll notice that some parts of it are red and some parts of it are black. What do you think that stands for? My part is unstable. Remember that we said that not only is computing the fixed point, the position of the fixed point, what x and what v and what w it is fixed point for is important. What is also important is to find what happens to trajectories in the neighborhood, and you can actually get that directly from XPP. It's a calculation of linear stability analysis, and auto will do that calculation for you as it plots the branch of fixed points as well. Well, that is very convenient because it says that if I am in the neighborhood of this red piece over here, so that is to say any position of the fixed point from here to here will have a attraction to it, will have an attractive stability, that is it will be stable, it will attract nearby trajectories. In this region something interesting is happening, we don't know what, but we know that the fixed point is unstable. Something will happen, we don't know exactly what. At the moment we don't know what, but something will happen so that if you start in the neighborhood of that fixed point in this region over here, like for example 8, the position marked 8, you will not converge towards the fixed point. You will go, something else will happen. Okay, so we will have to ask what happens. It's obviously very curious to me, to you as well. And then somewhere over here again you got a branch of stable steady state. Okay, so that was the surprise. That was that is incredible. I mean, that is saying that, well, you are in a resting position when you have low stimulation. If you stimulate a little bit with a little bit more tonic current, you are also in a resting position, but just a different resting position. You rise in voltage from here to here. But this is interesting. If you increase the current way high, there comes a point beyond which if you increase the current, you are again stationary. The voltage does not change anymore. The voltage is a fixed point, and it's an attractive fixed point. Right? Amazing. That's just, I still get surprised even though I've seen it so many times. Okay, so what's happening in between? What's happening in the region where the fixed point itself is unstable? Anybody? You think there could be a limit cycle? Okay, good guess. There could be a periodic orbit. Okay. Okay, that's your guess. Good. Anybody want to take another guess? There are two bifurcations, yes. For those of you who know bifurcations, this is a good exercise in asking what kinds of bifurcations you will have. There are two Hopf bifurcations. But don't worry, those of you who are not following what the discussion is. What do you think is happening? Anybody else from the other than the ones who have already seen bifurcations before? Bifurcation points, Hopf bifurcations. Just take a wild guess. It doesn't have to be accurate, right? Those answers were not accurate, by the way, so you don't have to feel bad. What do you think could be happening? What can possibly happen if your fixed point becomes unstable? Any guess? You might find a periodic orbit is taking place. What could be the connection between the periodic orbit and the fixed point being unstable? Well, let's find out. Okay, shall we? And you'll find that the answer is subtle. It's actually quite interesting. How many people think that if your fixed point becomes unstable, which means to say the fixed point is no longer attracting trajectories nearby, when the trajectories have to do something else, so they could go into an oscillation. At this position over here, for example, I might find an oscillation, boom, 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 right? How many people think that is correct? Okay, raise your hands clearly if you think that is correct. If you don't think it's correct, then I will have to ask you what else could it possibly be. So I see a few hands go up and down. That's an oscillation, but I would like not to see an oscillation. Okay, only a few people are convinced by that argument. Why is that? You'd rather see it. Okay, fine. You'll see it. We'll see what happens. No. Okay, so you'll see it when you see it. So here's what we'll do. I'll go on and click grab. Grab. I'm using my tab to go move along this, okay? And I'm also watching this space over here. When I reach what is called the Hopf point, Hopf bifurcation HB will show up, okay? Ready? There you go, there it is. Okay, you see this Hopf bifurcation? I'm at this position over here, and there is something distinguished about this position. That is the position where the stability of the fixed point is changing. That is the exact position where the stability. So there's a critical point over here. There's a critical transition over here, and that position is known to Otto as a Hopf point. You know, something dramatic is happening over here, and in particular, at this stage, we know that the fixed point, the stable fixed point, is becoming unstable as passing through this position. Okay, is everyone okay with this? That's a distinguished position called the Hopf position. So when I find the Hopf position, I'm going to click enter, and in fact, if you look at this table over here, you actually get a hint that there is a second Hopf. Where do you think the second Hopf is? Over there. That's probably where it is, right? You can actually check it. It's going to be labeled 12. Label 12 appears here, right? Okay, so that's going to be a second Hopf. We'll worry about that Hopf later. Let's talk about this Hopf point and ask ourselves, what is the behavior that will happen as you pass across the Hopf point? Okay, so I have gone over to the Hopf point and I've clicked enter, so that I have grabbed that point. Grabbing that point means XPP now Auto now knows I'm going to start with this. What do you mean by start? Okay, let's take a look. And I will click on run, but this time I will not look for steady state. I will look for periodic orbits. Remember, see this first option over here? That is a periodic orbit. I'm asking, if you think that this is a distinguishing point, is there a periodic orbit? Is there a branch of periodic orbits that is present in the neighborhood of this diagram? In this diagram, as I pass through the stability, do you think, I'm asking Otto, do you think that there could be a branch of periodic orbits that might be there that I could be switching on to? So in other words, as I pass through this, the unstable period, the fixed point becomes unstable, but maybe there is a periodic orbit that the system can be stable into, which means that I know that if I start near the unstable fixed point, in the neighborhood of it, I will diverge away. But maybe there's a periodic orbit that is attracting, and I can now go live on that periodic orbit as I move away from the unstable fixed point. Okay, so that's my hope, my expectation, or my guess, my wild guess. But all I'm asking Otto to do is to look for periodic orbits in the neighborhood of the Hopf point. That's what I'm asking you to do. Okay, and I'll show you in a minute, or let me do it first and then I'll describe it to you. Okay, so let's click periodic orbit, and cross our fingers and let's hope it does the calculation. Whoa, okay. So you'll see that there's a whole bunch of numbers that are keep on floating over here. Auto sometimes doesn't know when to stop. So basically it computed these branches, whatever these branches are, and kept going, producing the same thing over and over again. So I had to go click abort, stop, you've done what you needed to do. Okay, that's a quirk of auto. Now I'll go in and axes fit them. Okay, there it is. Okay, so we see something interesting. Now we've seen branches of periodic orbits. Some of them are colored in green and some of them are colored in blue. But what do these mean? What do I mean branches of periodic orbit? Just like these were branches of fixed points, I have branches corresponding to periodic orbit, which means the following. If I pick this parameter value I naught and I pass like so, I will find my unstable fixed point, and I will also find these 2 points corresponding to the maximum and minimum. Remember your high low, maximum and minimum of a periodic orbit at that value of I0. Okay, got it? So this green branch, this point and its corresponding upper point at that value of I0 corresponds to a periodic orbit and a stable periodic orbit, a limit cycle. That is to say, if I am here and in the neighborhood, I will converge to this oscillation represented by these 2 maxima and minima. Okay. Now what about these guys over here, this blue stuff? The blue stuff are actually unstable periodic orbits. They are also periodic orbits. Like for example, if we pick this point and the corresponding point at the same I0, that point and that point will correspond to a periodic orbit. But now that periodic orbit is unstable. That means if you start off of it, you will no longer converge back to the periodic orbit you started from, you will go to something else. Okay. So in passing through the Hopf bifurcation, as you move into the region, this entire region over here where you have unstable fixed points, and if you're exactly on the unstable fixed point, fine, you will stay there. The moment you make a perturbation away from that, you will actually switch into the corresponding periodic orbit. Okay, so I'm going to show this to you right now, just for 2 reasons. One, to show you that you can take this diagram and plot its trajectory, behavior and XBB, and 2, to show you that, to convince you that I am really telling you what I am telling you, so that you can cross check what I am saying. Okay, so I'm going to do the following. I'm going to go grab. I'm going to go to 7. The position 7, I'm going to say enter. Position 7 is exactly on the fixed point, right? So if I plot this in XBB, what should I expect to see? I should expect to see a stationary trajectory in voltage or W, right? Okay, so let's see whether if I can see that. I will change this. I've already grabbed it, so now both XPP and auto know it. So I'm going to simply use that as my initial condition, but I need to change my view axes. Xi versus t, I'm going to make it V because I'd like to plot V. Okay, so oops. Okay, so here's what I'm saying. If using that point, if I plot it for a long time, I see a stationary solution, and then something happens that I start seeing these big oscillations. I see a stationary solution and then this series. Now, can somebody explain this curve to me? I will do this. I will continue this to 250. Sorry. Or maybe even 300. Okay, and I want you to look at this diagram and explain it to me in terms of the bifurcation diagram that I started out with. I started at 7, I grabbed this position 7, and I'm plotting the trajectory corresponding to what happens if I start at the position 7. For a long time, I see a flat line, which is expected because if I'm at the stationary solution, I will stay at the stationary solution. But then I should have stayed at the stationary solution. It's at a fixed point. I'm at a fixed point, right? What happened? The point is unstable. So even if there is numerical instability, there's something that a little bit of numerical instability moved you away from the fixed point. And if you moved away from the fixed point, apparently it's happening somewhere in this region. As you move away from the fixed point, I switch my attractor. That is to say, I move from being away from this position to the only other attractor that is stable at that position of at that value of I0, and that attractor is actually a periodic orbit. Okay, so I moved, because of numerical instability, from a fixed point towards the other periodic orbit oscillator at that same value of I0. That's what's happening. Okay, so I'd like you to convince yourself, if I had controlled for numerical instability by making my numerical approximation scheme a little bit more sophisticated, picking a higher order method, reducing my step size, I can actually get this line to go whoop, far out. I can control for the numerical instability, I can play around with those parameters that will refine my numerical solution, and I can watch this stable solution go out for much longer, okay, before the numerical instability actually kicks in. Okay. So this is describing to you that yes, auto does a very good job of capturing unstable fixed points, right, and you can pick them up in XPP, and it also says that look, if there was some perturbation that came along and kicked you off the fixed point, you would actually jump into a periodic orbit, and that's what's shown over there. Okay, so we'll stop here for now. Let's go over for tea, and we'll come back and continue this tomorrow. Yeah. 2 questions. What's yours?